A meander, in general, is a bend in a sinuous watercourse or river. A meander forms when moving water in a stream erodes the outer banks and widens its valley, and the inner part of the river has less energy and deposits silt. A stream of any volume may assume a meandering course, alternately eroding sediments from the outside of a bend and depositing them on the inside. The result is a snaking pattern as the stream meanders back and forth across its down-valley axis. When a meander gets cut off from the main stream, an Oxbow Lake forms. Over time, meanders migrate downstream, sometimes in such a short time as to create civil engineering problems for local municipalities attempting to maintain stable roads and bridges. There is not yet full consistency or standardization of scientific terminology used to describe watercourses. A variety of symbols and schemes exist. Parameters based on mathematical formulae and numerical data vary as well, depending on the database used by the theorist, unless otherwise defined in a specific scheme. Meandering and sinuosity here are synonymous and mean any repetitious pattern of bends or waveforms. In some schemes, meandering applies only to rivers with exaggerated circular loops or secondary meanders, that is, meanders on meanders. Sinuosity is one of the channel types that a stream may assume over all or part of its course. All streams are sinuous at some time in the geologic history over some part of the length. Origin of term. The term derives from the Meander River located in present-day Turkey and known to the ancient Greeks as mu alpha iota alpha nu delta rho omicron sigma meandros, characterized by a very convoluted path along the lower reach. As such, even in classical Greece the name of the river had become a common noun meaning anything convoluted and winding, such as decorative patterns or speech and ideas, as well as the geomorphological feature. Strabo said, "Its course is so exceedingly winding that everything winding is called meandering." The Meander River is located south of Izmir, east of the ancient Greek town of Miletus, now Millet, Turkey. It flows through a graben in the Meanders Massif, but has a floodplain much wider than the meander zone in its lower reach. Its modern Turkish name is the Büyük Meanders River. Meander geometry. The technical description of a meandering watercourse is termed meander geometry or meander planform geometry. It is characterized as an irregular waveform. Ideal waveforms, such as the sine wave, are one line thick, but in the case of a stream the width must be taken into consideration. The bankfill width is the distance across the bed at an average cross-section at the full stream level, typically estimated by the line of lowest vegetation. As a waveform, the meandering stream follows the down-valley axis, a straight line fitted to the curve such that the sum of all the amplitudes measured from it is zero. This axis represents the overall direction of the stream. At any cross-section the flow is following the sinuous axis, the centerline of the bed. Two consecutive crossing points of sinuous and down-valley axes define a meander loop. The meander is two consecutive loops pointing in opposite transverse directions. The distance of one meander along the down-valley axis is the meander length or wavelength. The maximum distance from the down-valley axis to the sinuous axis of a loop is the meander width or amplitude. The course at that point is the apex. In contrast to sine waves, the loops of a meandering stream are more nearly circular. The curvature varies from a maximum at the apex to zero at a crossing point, also called an inflection, because the curvature changes direction in that vicinity. The radius of the loop is the straight line perpendicular to the down-valley axis intersecting the sinuous axis at the apex. As the loop is not ideal, additional information is needed to characterize it. The orientation angle is the angle between sinuous axis and down valley axis at any point on the sinuous axis. A loop at the apex has an outer a convex bank and an inner a concave bank. The meander belt is defined by an average meander width measured from outer bank to outer bank instead of from centerline to centerline. If there is a floodplain, it extends beyond the meander belt. The meander is then said to be free. It can be found anywhere in the floodplain. If there is no floodplain, the meanders are fixed. Various mathematical formulae relate the variables of the meander geometry. As it turns out, some numerical parameters can be established, which appear in the formulae. The waveform depends ultimately on the characteristics of the flow, but the parameters are independent of it and apparently are caused by geologic factors. In general, the meander length is 10 to 14 times, with an average 11 times, the full bank channel width and 3 to 5 times, with an average of 4.7 times, the radius of curvature at the apex. This radius is 2 to 3 times the channel width. A meander has a depth pattern as well. The crossovers are marked by riffles, or shallow beds, while at the apices are pools. In a pool, direction of flow is downward, scouring the bed material. The major volume, however, flows more slowly on the inside of the bend where, due to decreased velocity, it deposits sediment. The line of maximum depth, or channel, is the Talweg line. It is typically designated the borderline when rivers are used as political borders. The Talweg hugs the outer banks and returns to center over the riffles. The meander arc length is the distance along the Talweg over one meander. The river length is the length along the center line. Formation. Meander formation is a result of natural factors and processes. The waveform configuration of a stream is constantly changing. Fluid flows around a bend in a vortex. Once a channel begins to follow a sinusoidal path, the amplitude and concavity of the loops increase dramatically due to the effect of helical flow sweeping dense eroded material towards the inside of the bend, and leaving the outside of the bend unprotected and therefore vulnerable to accelerated erosion, forming a positive feedback loop. In the words of Elizabeth A. Wood, "This process of making meanders seems to be a self-intensifying process, in which greater curvature results in more erosion of the bank, which results in greater curvature. The cross-current along the floor of the channel is part of the secondary flow and sweeps dense eroded material towards the inside of the bend. The cross-current then rises to the surface near the inside and flows towards the outside, forming the helical flow. The greater the curvature of the bend, and the faster the flow, the stronger is the cross-current and the sweeping. Due to the conservation of angular momentum, the speed on the inside of the bend is faster than on the outside. Since the flow velocity is diminished, so is the centrifugal pressure. However, the pressure of the super-elevated column prevails, developing an unbalanced gradient that moves water back across the bottom from the outside to the inside. The flow is supplied by a counterflow across the surface from the inside to the outside. This entire situation is very similar to the tea-leaf paradox. This secondary flow carries sediment from the outside of the bend to the inside, making the river more meandering. As to why streams of any size become sinuous in the first place, there are a number of theories, not necessarily mutually exclusive. Stochastic theory. The stochastic theory can take many forms, but one of the most general statements is that of Scheidegger. The meander train is assumed to be the result of the stochastic fluctuations of the direction of flow due to the random presence of direction-changing obstacles in the river path. Given a flat, smooth, tilted artificial surface, rainfall runs off it in sheets. But even in that case, adhesion of water to the surface and cohesion of drops produce rivulets at random. Natural surfaces are rough and erodible to different degrees. The result of all the physical factors acting at random is channels that are not straight, which then progressively become sinuous. Even channels that appear straight have a sinuous-style wag that leads eventually to a sinuous channel. Equilibrium theory. In the equilibrium theory, meanders decrease the stream gradient until an equilibrium between the erodibility of the terrain and the transport capacity of the stream is reached. A massive water descending must give up potential energy, which, given the same velocity at the end of the drop as at the beginning, is removed by interaction with the material of the stream bed. The shortest distance, that is, a straight channel, results in the highest energy per unit of length, disrupting the banks more, creating more sediment and degrading the stream. The presence of meanders allows the stream to adjust the length to an equilibrium energy per unit length in which the stream carries away all the sediment that it produces. Geomorphic and morphotectonic theory. Geomorphic refers to the surface structure of the terrain. Morphotectonic means having to do with the deeper or tectonic structure of the rock. The features included under these categories are not random and guide streams into non-random paths. They are predictable obstacles that instigate meander formation by deflecting the stream. For example, the stream might be guided into a fault line. Associated landforms. Slip-off slope. On the inside of a meander is a gentle slope of sedimentation referred to as the slip-off slope. It is often marked by a point bar in the river. River cut cliff. On the outside of a meander, the river cuts into the bank, often resulting in a river cliff, also known as a cut bank or a bluff. Erosion mechanics. Most meanders occur in the region of a river channel with shallow gradients, a well-developed floodplain, and cohesive floodplain material. Deposition of sediment occurs on the inner edge, because the secondary flow of the river sweeps and rolls sand, rocks and other submerged objects across the bed of the river towards the inside radius of the river bend, creating a point bar below the slip-off slope. Erosion is greater on the outside of the bend where the soil is not protected by deposits of sand and rocks. The current on the outside bend is more effective in eroding the unprotected soil, and the inside bend receives steadily increasing deposits of sand and rocks, and a meander tends to grow in the direction of the outside bend, forming a small cliff called a cut bank. This can be seen in areas where willows grow on the banks of rivers. On the inside of meanders, willows are often far from the bank, whilst on the outside of the bend, the roots of the willows are often exposed and undercut, eventually leading the trees to fall into the river. This demonstrates the river's movement. Sumping usually occurs on the concave sides of the banks, resulting in mass movements such as slides. Deposits. Point bars are simply an accumulation of deposited alluvium that collects on the inside bank of a meander curve. This accumulation occurs due to the stream's lower velocity in the interior portion of the curve. In accordance with the Joulstrom curve, sediment will settle more readily at lower velocities. Point bars typically are composed of sediment ranging in size from pebbles to granular sands. Only in still water do silt particles settle. Incised meanders. If the slope of an established meandering stream is suddenly increased, it will resume downward erosion. This happens when the base level of the stream is reduced, for example due to tectonic uplift of the region, a global fall in sea level, collapse of a moraine-dammed lake downstream, or by capture of the stream by a steeper one. Is the stream eroded erodes downwards, its established meandering pattern will remain as a deep valley known as an incised meander or entrenched meander. Rivers in the Colorado Plateau, the Kentucky River Palisades in central Kentucky, and streams in the Ozark Plateau are noted for these incised meanders. Oxbow Lakes are created when growing meanders intersect each other and cut off a meander loop, leaving it without an active cutting stem. This process is usually linked to flooding, where the river will tend to the path of least resistance. The oxbow, being of much lower energy than the more direct path, collects more and more deposited sediment each season of flooding until it becomes independent from the river. The largest oxbow lakes will be in areas with wider flood plains where the rivers have more room to meander. Over a period of time, these oxbow lakes tend to dry out or fill in with sediments. Abandoned meander. Sometimes an incised meander is cut off, similar to an oxbow lake. The resulting landform is known as an abandoned meander. In the southwest United States, it is also known as a rincon. One dramatic example on Lake Powell is called the Rincon. Scroll bars are a result of continuous lateral migration of a meander loop that creates an asymmetrical ridge and swale topography on the inside of the bends. The topography is generally parallel to the meander, and is related to migrating bar forms and back bar chutes, which carve sediment from the outside of the curve and deposit sediment in the slower flowing water on the inside of the loop, in a process called lateral accretion. Scroll bar sediments are characterized by cross-bedding and a pattern of fining upward. These characteristics are a result of the dynamic river system, where larger grains are transported during high-energy flood events and then gradually die down, depositing smaller material with time. Deposits from meandering rivers are generally homogeneous and laterally extensive, unlike the more heterogeneous braided river deposits. There are two distinct patterns of scroll bar depositions: the eddy accretion scroll bar pattern and the point bar scroll pattern. When looking down the river valley, they can be distinguished because the point bar scroll patterns are convex and the eddy accretion scroll bar patterns are concave. Scroll bars often look lighter at the tops of the ridges and darker in the swales. This is because the tops can be shaped by wind, either adding fine grains or by keeping the area unvegetated, while the darkness in the swales can be attributed to silts and clays washing in during high water periods. This added sediment, in addition to water that catches in the swales, is a favorable environment for vegetation that will also accumulate in the swales. Derived quantities. The Meander Ratio, a Sinuosity Index, is a means of quantifying how much a river or stream meanders. It is calculated as the length of the stream divided by the length of the valley. A perfectly straight river would have a meander ratio of 1, while the higher this ratio is above 1, the more the river meanders. Sinuosity indices are calculated from the map or from an aerial photograph measured over a distance called the reach, which should be at least 20 times the average full bank channel width. The length of the stream is measured by channel or talweg length over the reach, while the bottom value of the ratio is the down valley length or air distance of the stream between 2 points on it, defining the reach. The Sinuosity Index plays a part in mathematical descriptions of streams. The index may require elaboration, because the valley may meander as well, i.e., the down valley length is not identical to the reach. In that case, the valley index is the meander ratio of the valley, while the channel index is the meander ratio of the channel. The channel sinuosity index is the channel length divided by the valley length, and the standard sinuosity index is the channel index divided by the valley index. Distinctions may become even more subtle. Sinuosity Index has a non-mathematical utility as well. Streams can be placed in categories arranged by it. For example, when the index is between 1 and 1.5, the river is sinuous, but if between 1.5 and 4, then meandering. The index is a measure also of stream velocity and sediment load, those quantities being maximized at an index of 1. Bibliography. Hicken, Edward J. Meandering Channels. In Middleton, Gerard V. Encyclopedia of Sediments and Sedimentary Rocks. Kluwer Academic Encyclopedia of Earth Sciences. Dordrecht, Boston. Kluwer Academic Publishers. pp. 430-434. ISBN 1-4020-08724. Leopold, Luna B. Langbain, W. B. River Meanders. Scientific American, 60. Virtual Luna Leopold, Thoniumin, P. The Meander Valley, A Historical Geography from Antiquity to Byzantium.